Hi everyone, this is Lunlong Li, and together with Kunhan as well as Shuhao Li, I'm delighted to present our work titled Evaluation of Manifold Learning Methods for Fashion-Mixed Embedding. This study explores how different dimensionality reduction techniques perform in embedding high-dimensional image data, using the challenging fashion-mixed dataset as a benchmark. And fashion-mixed, unlike the original mixed dataset of handwritten digits, it consists of grayscale images of clothing items. This makes it more complex and representative of real-world image data, with a nonlinear structure and high-dimensional nature that makes it ideal testbed for manifold learning algorithms. And our objectives are to compare the ranking performance of 7 popular manifold learning methods and to quantify how well each method's one-dimensional ordering aligns with the true label using Kendall's tool correlation coefficient, and to investigate which method suits the real world and the textured images like fashion mixed best. And we evaluated 7 methods including diffusion map, MDS, isomap, LLE, MLLE, TSNE, and UMAP. And we use KDCC for ranking quality and visualization to assess the embedding performance. Here, you see 51 randomly selected images from our 500 sample subset in shuffled order. And on the bottom, the images are arranged by their true labels. A good embedding method should produce a similar ordering automatically like this. And for the first method, diffusion map is a nonlinear embedding technique that uncovers the intrinsic geometry of data by simulating a random walk on the graph of pairwise similarities. It is particularly effective at capturing global structures in the data. While robust to noise, its computational cost is also high. And in our results, diffusion map achieves a KDCC of 0.38, showing partial grouping but poor global alignment. Second, we examined multidimensional scaling methods, which minimizes stress between pairwise Euclidean distances, and it preserves global pairwise relationships. While it performs moderately better, it struggles with local neighborhood preservation. It achieves a KDCC of 0.56, producing clearer clusters than diffusion map, but still overlapping some classes. And third, we tried isomap, which extends MDS by approximating geodesic distances on the data manifold using the k-nearest neighbor graph. This allows it to better capture global structure while maintaining some local relationships. And it achieves a KDCC of 0.45, showing coherent stretches of similar items, though some boundaries still remain fuzzy. And then LLE, which is short for locally linear embedding, preserves local relationships by reconstructing each data point as a linear combination of its nearest neighbors. This is achieved by minimizing the reconstruction error, ensuring that the weights capture local geometry are invariant to translations, rotations, or scaling. And it performs moderately better, achieving a KDCC of 0.54. It demonstrates strong local grouping, effectively capturing neighborhood structures, but struggles with global ordering, leading to distortions in the overall embeddings. And then the modified LLE improves on LLE by estimating a local tangent space at each point and computing reconstruction weights within the tangent space, reducing the distortion when data curvature varies. However, in our results, MLLE still struggled with global alignment, achieving a slightly improved KDCC of 0.56. While MLLE better handles local curvature, it does not fully resolve the challenge of global structure preservation. Then, we tried TSNE, which is a popular method that excels at capturing local neighborhood relationships and forming tight clusters. It maps high-dimensional affinities to low dimensions by matching similarity distributions. And despite the cost of hyperparameter tuning, TSNE achieved a KDCC of 0.58, showing excellent local clustering but still poor global rankings. And then we also try linear method like PCA that projects data onto orthogonal directions of maximal variance. While PCA is computationally efficient, it struggles with nonlinear nature of the fashion mixed dataset, and then it achieves the lowest score with KDCC of only 0.24. This highlights its limitations for datasets with complex topologies. Lastly, we examined UMAP, which effectively preserves both local and global structures by optimizing the fuzzy simplical complex. It balances these structures better than other methods, making it particularly suitable for tasks like clustering and retrieval. After tuning, UMAP achieved the highest KDCC of around 0.60, producing clear class segments that closely match the ground truth. To sum up, our study highlights the strengths and limitations of various manifold learning techniques for embedding the fashion mixed dataset. Through our experiments, UMAP stands out as the best performing method, effectively preserving both local and global structures, making it ideal for embedding the fashion mixed images. And TSNE excels at capturing local neighboring relationships and forming tight clusters, but still struggles with global ranking. Diffusion map and ISO map are effective at capturing global structure but face challenge with scalability and local alignment. And then MDS, LLE, and MLLE show moderate performance with trade-offs between local and global preservation. And finally, PCA, as a linear method, while it is computationally efficient, is unsuitable for datasets with nonlinear structures like fashion mixed. And these findings emphasize the importance of selecting the appropriate manifold learning techniques based on datasets, characteristics, and specific goals for the embedding task. And future work will extend this study to larger subset and explore hybrid approaches or integration with deep learning to further enhance the embeddings. And this is the end of our presentation. Thank you for your attention.